Our next speaker is Professor Debashree Ghosh from Indian Association for the Cultivation of Science. So Debashree did a PhD from Orbital University, and then she moved to University of Southern California for her postdoc. And after that, she came back to India and joined National Chemical Laboratory in Pune. And then in 2017, she joined Indian Association for Cultivation of Science, and where she is a professor now. So Debashree has won many honors and fellowship. And I'd like to mention the annual medal of the International Academy of Quantum Molecular Science, which she won last year. And today I came to know that Debashree won Cone Prize, right? From ICTP, right? So with this, I think Debashree is going to tell us about matrix product states and so on.
So firstly, let me thank the organizers for giving me this opportunity. I'm going to talk about something very different, I guess. I am a chemist. Yeah, we also developed some methods that can deal with strongly correlated systems, because after all, the excited states are strongly correlated. Once we have developed those methods, we apply to systems that we like, such as photoprotection in melanin. We look at some spectroscopic properties. Of late, we have been interested in singlet fission, but I'm going to explain a little bit about some of the systems at first, and how and what are the kind of phenomena we might be interested in, how they connect to stuff. So yeah. So just to explain the idea of singlet fission in a little bit, is if I have two chromophores sitting very next to each other, and one shines light on it, one of the chromophores can get excited to the optically active singlet state of that chromophore. Now, since the chromophores are adjacent to each other, and if certain energy conditions are fulfilled, then essentially it can form two triplet states. But this, because there are two triplet states which are kind of coupled to each other, if one is pointing down, the other is pointing up over here, they actually form a singlet state in total. And so this is a spin allowed process, and it can happen in a reasonably facile way in certain molecules that obey these energy conditions. It's basically a potential energy surface that might look like something like this. So if one were to look at, try to understand this mechanism, or like I mentioned just a while back, if I were to look at the photoprotection in some biological molecules such as melanin. Now this is actually the spectra, the blue one is the high vacuum spectra of eumelanin. And as you can see, it's a very featureless spectra. So if one asks the question of why is it so monotonic and featureless, and what happens when it absorbs UV visible light? So these kind of questions. Another question one can, I mean, the kind of methods we develop that they can kind of approach are things such as light-induced spin crossover phenomena, or these magnetic systems even. If we were to, so as an inorganic chemist would basically synthesize a molecule like this pretty naturally. And they will talk about those J couplings, which are essentially the J parameters in a Heisenberg model Hamiltonian. And they will be able to even experimentally obtain those J parameters. And if I were to look at what is the phenomena that arises due to those different J coupling elements that are next to each other. And none of these these systems, they are not very uniform in many ways. There's different molecular entities, different atomic entities that are next to each other. So that's the kind of system one looks at, and the processes or phenomena that arises looks a bit complicated, but this is essentially what that looks at like. So let's say you have a nice ground state, which is reasonably far away from the excited state, which is generally how it happens in molecular systems, because you have the effect of confinement. So essentially mostly you will have the excited states reasonably far away from the ground state. But once you have excited to an optically active state, there's very many different pathways it can take. There are crossings of singlet and singlet states, singlet and triplet states, and so on, that can be encountered by that excited molecule, and it can lead to various photoproducts, or it can even come back to this reactant light source. So that's essentially the questions one would try to answer in a group like ours. It's really not, and we have to essentially be able to give reasonable estimates of the time scales of these relaxation and stuff like that, because after all, let's say if I come back to this melanin question, this is how we get protected from the sunlight. Our body protects us from the sunlight by those processes. So if it's below certain time scales will it be possible. Otherwise, it's going to go towards some photoproduct formation, and the melanin will become deactivated, which of course doesn't happen to normal human beings if they are in a healthy tissue. So those kind of processes we would like to look at. Now, what is a general, as a quantum chemist, what are the elements in our toolbox that we use to study such systems? Well, in short, basically we have the repertoire of single reference quantum chemical methods, and using that, we'll basically look at snapshot by snapshot. In fact, we'll look at dynamics in that way along different snapshots of the molecule as it goes along in time. But to solve the underlying electronic structure problem, one starts from a Born-Oppenheimer approximation, where they, if it is really not making sense, please do let me know, because I do know that my language is very different. Okay, so first we start with a Born-Oppenheimer approximation, which says that, okay, I have the nuclei and the electrons, and since the nucleus is mostly reasonably heavier than the electrons, then they are going to be almost frozen in that time scale. So that's the Born-Oppenheimer approximation. And using that, I'm just going to take out the electronic problem out. After I take the electronic problem out, I'm going to apply some kind of a mean field approximation. It could be Hartree-Fock in most cases, at least in the cases in my group, we always use Hartree-Fock kind of techniques. One could choose to use DFT. After we have taken this mean field approximation, of course, in this mean field approximation, there's no electron correlation, which is far from reality. Electrons are correlated, they see each other, they avoid each other. So in order to correct for that, one would use some perturbative approximation, or at least, how should I put it, incremental approach, even if it's not perturbative. For example, if I were to do a configuration interaction on top of Hartree-Fock, you would take more and more configurations into that wave function, but still that would be an incremental way. I wouldn't say I am going to take the full Hilbert space and try to solve something in that, because for most of these molecular systems, the full Hilbert space is excruciatingly large. Okay, so that's what's going to be the first approach of a quantum chemist. Now, the problem that's going to arise is, well, it fails in many situations, and more importantly, it fails even in chemical reactions in many cases. For example, I take a very small molecule. Again, I know many of you are scared of molecules, but still this is a very small one, right? It's a water molecule, and I'm pulling apart the bonds. If I pull apart the bonds, I expect the energy to change like this black curve, right? When it goes to infinite separation, essentially the bonds are broken. I have those oxygen atom, hydrogen atoms, they are not interacting with each other. It should go to some energy smoothly. But what happens for the perturbative approximations or the coupled cluster, another incremental approximation that was mentioned in the previous slide, this is what the curve starts looking like, which is qualitatively horrible. I mean, it's so wrong. If you look at the errors, this is what the errors look like, and at bond breaking, which is something a chemist is, passionate about. We want to break bonds and make bonds, right? So at that point, there's infinite error. So that's an infinite disaster. Okay, MP2 is molar placet perturbation, which is essentially you are adding, you have a 2 electron, so you have done the Hartree-Fock solution. For that, you have found the molecular orbitals. Once you have found the molecular orbitals, if you have the 2 electron term squared, and on the denominator, you have an energy gap. That's all you have. So basically what you're doing is, I have found a bunch of orbitals. Orbitals are 1 electron wave functions, but in reality, the wave function shouldn't be 1 electron wave functions. So how will I correct each of those 1 electron orbitals for the effect of correlation? If that's how you would like to think at, that's what MP2 would do. Coupled cluster, on the other hand, says that, okay, I'm going to change the wave function. So after I've found the Hartree-Fock wave function, which is just a product form, if I multiply that in front with an exponential operator, exponential of excitation operators. So the excitation operators are going to give me either a single excitation or a double excitation or so on. If I have an exponential of a excitation operator, that's going to give me the singles, single square, singles cube, and so on. Similarly, doubles, doubles cube, double square, blah, blah, blah. So essentially, you have access to all sorts of excitations, but they're coupled. You can't tune each of those terms separately. So you have a finite number of equations, but an excitation that goes up to whatever number of electrons that you have left. Okay, so that's essentially what these methods refer to. Unfortunately, quantum chemists are very used to many acronyms. Yeah, please stop me when I do that. Okay, but these are like the most often used methods that, first thing one would learn in a lab is these, and they do fail. This is what I'm showing for a small molecule bond breaking. Similar effects actually shows up for excited states, for diradicals, triradicals, transition metal complexes, polyenes, graphenes, metal clusters, pretty much every interesting system, it falls apart, this single reference method. So you might even ask the question, what is it good for? Well, actually, it so happens that in many cases, when the bond is not just completely broken, as in when a chemical reaction happens, a bond gets broken while another gets formed. So in that, I think somewhat cancellation of error also maybe, actually the energies are not terrible. If you are looking at reaction energies and stuff like that. So that's why people do use those single reference methods and do get away with using the single reference methods in many situations. But still, it will be horribly wrong in these more complicated stuff. Okay. So why is that going on? Of course, because that's the place where we are reaching the strong correlation regime. Because when we did those mean field approximation, what we kind of at the back of our mind presumed is that there are n number of orbitals which are filled and the rest of the orbitals which are unfilled. So again, at the back of our mind, I have made an assumption that there's a nice energy gap between the highest occupied orbital and the lowest unoccupied orbital, which many a times may not be true, especially if there's a lot of conjugation or if there are metals which has d orbitals which are close to each other. In those cases, this energy gap is going to be pretty low. And this whole assumption that a single configuration can actually give a good starting point is just flat out wrong. Okay. So even the starting reference is wrong. So whatever you do on that reference, you are going to get garbage multiplied by garbage. Okay. So again, lots of alphabets, but I'm going to walk you through this because sometime or the other I might be telling these alphabets. They're not very difficult to understand. So in the single reference frame of things for chemical problems, this is actually a textbook schematic that is given in many quantum chemistry books. Basically, what it says is, this is on the x-axis, you have the size of basis, and on the y-axis, you have the degree of correlation. Of course, if you took a full configuration interaction, which is the other way of saying an exact diagonalization, you have taken the full Hilbert space and have been able to diagonalize it. In a chemical problem, it's almost never possible. In a, molecular problem, it's almost never possible. And I have already explained Hartree-Fock, MP2, CCSD. Now, instead of singles and doubles, if you have taken singles, doubles, triples, excitation, blah, 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 you will go towards full CI. So that's basically the kind of correlation that you have increased from here. You're basically dialed on the correlation. And here you have dialed on the size of the basis, as in the size of the atomic orbital basis, because how you are building the molecular orbitals to begin with is from atomic orbital basis, and that atomic orbital you can choose to take, I only like 1s orbitals for hydrogen and forget about the rest, or I can say that I will take 1s, 2s, 2p, blah, blah, blah. So depending on that, basically you'll have a single zeta, double zeta, triple zeta, more and more and more. So if you have a complete basis, which is of course impossible, and if you have full CI, which is of course impossible, then you have the exact solution, which is of course, yeah, it's a theoretical thing. It's never going to happen to us. But another thing at this point, maybe I should point out is, again, cancellation of error is our friend. So sometimes if you use a bad enough method and bad enough basis, it actually gives wonders. So that's a wrong way of doing things, but many a times our systems are so large, we are pushed against the wall, and that's what we end up doing. That's the single reference frame of pictures. But when we are doing this in the multi-reference framework, in other words, when we have strong correlation, presence of strong correlation as well as dynamic correlation. See, dynamic correlation is always going to be present, and this terminology is not common, right? Static correlation and dynamic correlation. Okay. So correlation, we all know that electrons will avoid each other. So when the electrons are close to each other, they will really avoid each other, and that's the dynamic correlation. In a dynamic sense, they will avoid each other. Okay. But when you have these orbitals which are closer in energy, just because you cannot take a perturbative approximation, or you can think about it this way, that your starting assumption of molecular orbital picture becomes more and more horribly wrong. When you have a pseudo-degenerate situation, your highest occupied orbital is almost degenerate with your lowest unoccupied orbital. In those situations, you should be taking all possible configurations. That, in a very weird nomenclature, is called static correlation. It should really be called non-dynamic correlation. It has nothing to do with dynamic correlation. That's why people call it static correlation. Okay. So basically, this is the kind of correlation we can deal with. The dynamic correlation is kind of the correlation we can deal with in a single reference framework. And this is that, in other words, it can be dealt with perturbatively or in an incremental sense. For the other kind of correlation, you really have to take everything, or at least everything in the valence space. Valence space basically means the most important orbitals. In a chemist picture, it's going to be the most important orbitals, which so happens that it's going to be around the Fermi level, right? So that's where it's going to be. So if you add the static correlation of the valence space, that gives rise to methods such as CASSCF. The full form of this is complete active space, and then SCF. So essentially, the SCF method that you use to solve Hartree-Fock, you are going to use the same SCF method, except here you will not take a single reference, but you will take multiple references and then solve for the molecular orbitals that way. Okay? Yes? By reference, I mean electron configuration. For example, I took the reference that I have populated orbital number 1, 2, 3, 4 up to n. And then from n+1 onwards, everything was empty. That is one reference. Then if I take another excited determinant, that will be, or excited CSF, that would be another reference, and so on. So single reference versus multi-reference. And then on top of that multi-reference wave function, if you are now adding these corrections due to the dynamic correlation, because the dynamic correlation is anyways there. For whether you have static or not, you will always have dynamic correlation. Then in the limit, you again reach the exact full CI solution. But this is basically how you can reach there. Notice one more thing. If you are going to keep increasing this ad nauseum, for example, instead of CISD, you have CISD, T, Q, P, blah, blah, blah. At one point, you'll of course reach full CI. Same for CCSDs and this. Basically, you are increasing the degree of excitation. But of course, this picture is not sustainable if you have too many states that are near degenerate. Okay. Okay. So, doubles, yes. Yes, yes, yes. Okay. So we are in good shape with all the alphabets. Great. Now let's look at a problem and see what are the difficulties in solving a problem. For example, if I look at the singlet triplet gap of acenes, and here I am going to really look at the molecule. So this molecule is made up of carbon atoms and hydrogen atoms, and each of the carbon atom will have pz orbitals sticking out of the plane of the molecule, and these pz orbitals will form the pi and the pi star molecular orbitals, which basically form the valence space. The rest of the space is of course less important, but maybe not so less important that I can throw it away, because there will be some amount of sigma pi correlation. The electrons in the sigma orbital, they're not just sitting there, right? They are also there, and they are going to see the pi electrons, and they are going to act on it and things like that. So anyways, this kind of shows the classic failure of single reference methods. In 2004, DFT had predicted, simple plain vanilla DFT had predicted that there's a singlet triplet crossover in these molecules, which essentially means as I increase the size of the molecules, the triplet state becomes more stable than the singlet state. And however, in 2007, GMRT predicted that there was no such crossover. And the major effect for that absence of crossover was static correlation. In 2010, there was another group who came about, pumped in enough higher amount of dynamic correlation. See here, and I'm sure that there's still no crossover, but this time due to dynamic correlation. So this is a weird thing going on. So basically, the electrons don't care whether they are statically correlated or dynamically correlated. We have artificially separated the space into my important space and less important space. And depending on those definitions, basically you can think of A as static correlation as or A as dynamic correlation. And that's what you're doing. So if you increase the level of correlation, even in the dynamically correlated, I did something? Oh. Okay, so yeah. Basically, if you pump in enough degree of correlation, I mean enough higher degree of those excitations, then you can capture static correlation also. That's what happened in this 2010 paper. And in 2015, our group basically used a method which has a balanced description of both static and dynamic correlation. So we found both. There's no mystery going on over here, but it's basically we have to I mean, think what are the methods that one wants to apply. And if, I mean, you can, how should I put it? You can use a blunt tool to, you know, still poke a hole, but it will take you a whole lot more effort, that kind of a thing. So that's, you need to choose your tool properly. Yeah.
Talking about Singlet Triplet gas in that system.
Yes.
So it saturates at about, what we found was it saturates at about 0.7 or 0.8 eV. The triplet.
Yes. Yes.
We found that. And then you also find a crossover between the 2A and 1B states around 4 rings.
Oh, I didn't look at the bigger ones. Okay. I mean, higher states I didn't look at. I looked at grounds, just Singlet Triplet. Yeah.
4 or 5 rings there's a crossover in the 2A and the 1.
Okay.
That's
Yeah.
both one can get from PMI.
But on the other hand, here is the thing. If you are using DMRG and then perturbation, then you can, then quantitatively you will see the decay is a bit different. As in it goes to the similar kind of EV, but the decay is a bit different. Yeah. So. Okay. Now the next thing is, of course, what are the challenges in calculating this Singlet Triplet gap? I will take all possible CSFs. I will do an exact diagonalization. I will done with it. That's the first thing I had thought when, well, I started working on these systems. But it so happens that if you have 30 pi orbitals with 30 electrons, which is basically boils down to 30 carbon atoms, not such big of a system, nowhere near you know, decay to infinite system or anything like that. The CSF space, or the number of configurations that one needs to consider, is 10 to the power 33. That's already becoming a pretty large number. And to put it into perspective, if we were doing a matrix diagonalization, you know, in a not a very sophisticated way, and it had an n cubed scaling, that would be 10 to the power 99 operations. And again, just to put that into perspective, the number of atoms in the universe is 10 to the power 82. So this is a supercomputer nobody can afford, no matter who. Okay, so that's definitely leading to a problem. And the problem is basically that of the exponential scaling kicking in. And I'm sure Professor Ramshesha taught DMRG yesterday and today, so he has talked about this. So I'm going to use that and wiggle out of this description. Okay, so basically here I'm showing the spin. This is just a model spin state, as in each lattice site has a spin up or spin down. If it were an orbital, then the orbitals would have 4 possibilities, right? It can be unoccupied, it can be occupied with a upspin, it can be occupied with a downspin, or it can be doubly occupied. So instead of 2 to the power n, at that point, it will become 4 to the power n. Essentially, this is a d to the power n scaling, and the n, that is the system size, is on the exponent. So of course, that's going to be a pretty bad situation. And the reason for that is, again, the full CI wave function can be written in this form. And in the matrix product notation, this is essentially this comb-like structure where each of those dimensions, each of these n's orbitals basically can be written as each of the things sticking out of the many dimensional beast is what I would call it. This is very many dimensional, right? K-dimensional. Okay. Now, I am sure again tomorrow and day after you are going to have a much better, more in-depth introduction into matrix product states, but still just to use some of the nomenclature, I'm going to give a very small introduction of this. So if in the matrix product notation, I have a real or a complex valued number, that's basically a round object with no legs sticking out. If I have a single leg sticking out, of course, that's a vector. If I have two legs, it's a matrix. Many legs, it's a tensor of 5 dimensions. And if I were doing a matrix vector multiplication, and therefore I'm contracting over the J index, this is the J index, this is the index that is left, I. So that's it. If I were doing a trace, it will look like a headphone and so on. Okay, so if I were to go from this many dimensional beast or the full CI wave function, and I were to do a singular value decomposition in between any of the 2 dimensions. Now I can think of this second dimension, third, fourth, up to nth dimension as a single dimension. I can make that into a single dimension, like a very big index, which goes to many, many digits, maybe. And if I can do a singular value decomposition in between this index and this complex index, then this is all that it would look like. So this is my diagonal matrix. This is the U and this is the V. That's all that I have. And if I keep doing this singular value decomposition ad nauseum between each of those sites, I will arrive at an object that looks like this, which is essentially the matrix product state that is used, that Professor Ramshesha talked about in his lectures. And the the dimension of this object is n times d times m squared, and m being the number of states that you retain, let's say in DMRG or something else. Doesn't matter how you retain those m states, but yes.
And you are doing this left canonical.
Yeah.
For orthogonal function.
Yes.
You are doing only the left canonical form, no? So you are doing SBD from the left side.
I can do it from either side. That shouldn't matter. And it can be shown for the single dot DMRG that this can be exactly put into that. If you, instead of 2 dots, the left dot and the right dot, if you have a single dot DMRG, you can show that this can be done from either sides.
If I take the mixed canonical, then
Yeah.
what will be the what will be the change? If I somewhere I put the left canonical form and somewhere I put the right canonical form, and if I glue 2 of them, then what will be the change? Is it valid for the orthonormality condition? If I take this,
I don't see any problem as such, and I really don't see any problem as such. But I can think about it and get back to you if
Okay.
there's a
Okay.
better answer.
Okay.
Yeah. Okay. So, anyways, again, this nice pictorial depiction can also be shown as matrix times tensor of 3 indices times a tensor of 3 indices and so on. And I'm sure again, Professor Ramshesha showed this. So I will not go through DMRG. But essentially what I am trying to say is that DMRG gives us a good algorithm to determine these matrix product states, because originally what I showed is if I had that beast, then I can reduce it into smaller objects. But I can't even store that beast in some computer for a reasonable size system. And therefore, there's no way of going from that many dimensional object to a low dimensional object. It's always better to go from the low dimensional object and only keep the most important degrees of freedom. Okay, so that's how it addresses the problem of the exponential scaling. But it is in a kind of a linear fashion, right? We took one orbital, then, or rather one side, then another side, then another side. And this is fine if you have one orbital per side. But many a time, a molecule I would be looking at will look like this. And this is a dichromium with some ligand groups all around. And if that were the case, then there's no easy way of ordering those orbitals. And in that situation, what was shown is you can do a low M DMRG, and from that you can calculate which of the orbitals, or even from the seniority ordered. So seniority ordered configurations are basically if you have the Hartree-Fock determinant, then you take two electrons, you excite it to the first orbital. You again take 2 electrons, you excite it to the second orbital. So like this, if you are populating each of the orbitals such that they are closed shell configurations, those set of configurations are called seniority 0 configurations. So between those seniority 0, those are not exponentially scaling numbers, because those will scale as number of orbitals that I have in NO into NV. That is only the kind of configurations I can generate. From those configurations, if one looks at which of the off-diagonal elements are largest in size, they basically decide those are the strongest correlated, and the ones which are smallest in size, those are the least correlated. That's what this paper basically does, and that's a way to find out how to order those orbitals. Basically, keep the orbital that is strongest correlated next to it, and then the next strongest, and so on and so forth. Yes.
Entangled or like? So should the orbitals, the two orbitals which are entangled, should they be next to each other? That is,
the ones which are,
you should keep adding them first.
Yes, we should
in the
first
DMRG.
and then the next ones. Yes. Yes, actually, of late there are quite a few different approaches that have been proposed, but this one seems the most physically intuitive one, and this one kind of works for the maximum, cases. It's not like it does not break, but and by break I mean I have to keep a bigger aim. That's it. Okay. So again, so basically when we applied those approaches to the polyacenes, this was done in the Garnet group. It showed that there's an increase in the biradical and polyradical nature of the ground states of the polyacenes. Later on, we in our group we used again alphabet soup of methods. The alphabet soup I will explain a little bit actually. I don't know if from back you can see, it's called SF-TDDFT or SF-MP2 or SF-CCSD. So we had already talked about MP2 or DFT or CCSD. Now what is spin flip? SF is basically refers to spin flip. So what you can do is if you start with a triplet state, let's say I have only 2 orbitals and 2 electrons, and I start with a triplet state, that's actually that state is least correlated, as in that state has the least number of references that are possible, because you are having 2 spins which are either up spins or down spins. Okay, but now once you go from that to the singlet states to a one lower spin state, your amount of correlation increases. In other words, the number of references possible increases. So in other words, a single reference method such as MP2 or CCSD can handle those high spin states much easier than the low spin states. So you basically create a reference state, let's say a triplet state, a reference state which is done by a method which can deal single reference situations, and then use an operator which is a spin flip operator. What will a spin flip operator look like? It will be exactly an excitation or a de-excitation operator, except that it will go from alpha to beta or beta to alpha, depending on whatever is your notation. Okay, So basically, if you have an excess alpha spin, it will go from alpha to beta. In that ways, after that spin flip operation, the resultant state is a singlet state. So that's basically a cheap, poor man's way of adding some amount of multi-reference without having all possible configurations. And the spin flip CCSB has both single spin flips and double spin flips. Double spin flips meaning one spin flip operator added to basically spin conserving operator. So so if I have two dagger and two non-dagger operator, 3 of them will be alpha, 1 will be beta, like that. We used in the exponential operator, yes. Or even after the exponential operator, there is another place where we can use. So there's a formalism called equation of motion coupled cluster, which creates the coupled cluster wave function, the coupled cluster reference wave function, and then on top of it adds a linear operator. But this there's a different. I mean to say that this reference, R operator can be in the exponents, or it can be in the linear form, depending on, again, a different alphabet soup. Yeah. Yes.
Box means, because when you say that biradical and can see the box,
Polyradical nature.
polyradical, does it mean that you actually have the tendency to have free spin one halves? Or in the language of valence bond theory, you would say that there are long bonds.
I mean to say that if you calculate the number operator, you will get numbers, the occupation numbers of orbitals which are not 2 or 0, which are somewhere in between. So if you have occupation number 1 and 1,
That's in the molecular orbital representation.
Yes.
So you might get that even for linear polyenes. Why just polyacenes?
You will get for linear polyenes.
You'll get that for linear polyenes and anything. It's basically in the valence bond language, you are getting long bonds instead of just short bond structure. And as the size increases, the number of long bonded structures increases.
Yes.
Okay,
Yes.
you got it. Thank you.
Can you wind up in another 10 minutes so that we have some time for questions?
Okay. Okay, sure. I haven't gotten over my introduction, but that's fine. If I made sense to some people, I'm fine. In our group, we actually did the singlet triplet gaps for acenes, polyazulenes. These are 7-5 bond, ring, 7-membered ring, 5-membered ring systems, and 7-membered ring, 6-6-5, like those, because these are being synthesized as of late. And in these kind of molecules, we have seen that there is a singlet triplet crossover, which is a nice observation, fine. But once we go ahead and look at the correlation between the singlet triplet gap and the occupation number of the LUMO, which basically gives us an idea of how diradical or polyradical nature it is, because if you have an occupation number in the LUMO, that means you have a radical that is residing over there. We don't see a correlation. Now again, you may not be figuring out why I had expected this correlation to begin with, but let me give a simple orbital picture. So if I have a large homolumo gap, as in highest molecular orbital and lowest molecular orbital gap, versus a low one, then for the low one, basically the singlet triplet gap should be lower. That's what one would expect. But in the same way, you would also expect the electron to be able to populate these states much more for the singlet state than it would be for a situation where the the energy gap between these orbitals are much more. So it's this simple picture which made us expect that that singlet triplet gap will have a correlation with homolumo gap. And it so happens that in many of these acene systems, there is a nice correlation. But once we broke the, those nice 6-membered rings into 5-membered and 7-membered rings, we found that there was no correlation. And then we actually went to a talk which Professor Ramshesha was giving in IISc, and I came across this paper also where you were talking about this frustrated spin ladder systems. Of course, at that point, As a chemist, I did not know that these two systems were so similar, but they are, because the connections are really the same. And therefore, what I have to do essentially is to remove all the lattice degrees of freedom and all the details of the molecular Hamiltonian and break it down into a form that looks like this. This is a part I do want to talk a little bit about. So of late, we have been working quite a lot in building these molecular Hamiltonians from different quantum chemical methods for complicated systems, not just carbon hydrogen stuff. So here it shows that if I do a DMRG on a 7x2 and 5x2 system, basically this rule says that the Heisenberg J has correlation between energy gaps between two different spins, high spin and a low spin state. And if the high spin and the low spin state is taken to be 7x2 and 5x2 versus 5x2 and 3x2 and 3.5 and so on for this system, basically this is how it changes. And as you can see, if you keep increasing the M, these differences go down, and you indeed can get a value which is very close to the experimental value without doing some funny stuff. That's one way of doing these. The other way is actually to think what we are trying to do. So we have a big Hamiltonian, big molecular Hamiltonian, and we are trying to basically find out the eigenvalues and eigenstates of at least low-lying eigenvalues and eigenstates of those Hamiltonians. But if I were to somehow be able to transform this Hamiltonian into an effective Hamiltonian, where the spectrum, at least the low energy spectrum, remains the same, that's all that I want. Again, that boils down to decoupling the model Hamiltonian model part and the outer space part. Basically, if you can change, divide the space into a space that I like and I don't like. And I always think here a simple example is the Huckel Hamiltonian, where we take only the pi orbitals. And of course, I take very simple alpha and beta parameters, but let's not think about that. But still, what we are doing is we are making this assumption that I think the sigma and the pi don't talk to each other too much. I will take only the pi space and I will be done with it. That's one way of doing this decoupling and projecting into the model space. But if we were to do this rigorously even, there are several different ways of decoupling them. And Malview and co-workers had actually shown how to calculate this from the 2 electron integrals and the the hopping kind of terms and so on. We basically have shown kind of similar stuff from those spin flip methods that I talked about a while back. And the cool stuff that happens is because those two differences, the J basically is the difference between one spin and that spin minus one. So you can basically handle this by taking just a single spin flip operator. And a single spin flip operator has a low overhead. So basically, you can create these kind of configurations with respect to a up kind of a configuration. And you can even show this. So I have shown it for a very simple case where each site has a single spin. But if each site had multiple spins also, this thing works just fine, as has been shown with multiple chromium atoms and things like that. So if you take so there was a molecular magnet with 6 chromium atoms, and they did a spin flip calculation on dichromium, dichromium, dichromium like that. From that, you can basically take out those J parameters. And ideally, you can even find out those Hubbard parameters from the molecular calculations. So using that in our problem, we have seen that in fact why these fused ring systems were showing a singlet triplet crossover was because of these interactions due to spin frustration. And we also showed that that same effect is also seen in the molecular system, as in the molecular geometry relaxes in that way. And finally, using that, we have been able to formulate a computationally affordable method to screen the singlet triplet gaps of these systems and have some design principles and so on. However, what I really wanted to talk about was the extension to two-dimensional systems. I don't think there's any point in trying. Just to let you know that there was a 2017 science paper which shows that the tensor product state has a nice correlation with restricted Boltzmann machines, and we have therefore used this idea. So what this means is, I won't go into the details, I will not mention the results, but what restricted Boltzmann machines does, it's a neural network structure, but that's not the important part. The important part is if you give a distribution of some states as a input to these network, then what it gives back is the final distribution, as in you have only given some samples to it with certain probabilities, and it gives back the final distribution. So how does it do it? All it is doing is it is actually optimizing the Kullback-Leibler divergence parameter, which basically, even in the Bayesian language, it basically means what is my, what do I think of my prior, and what is, as in the prior distribution, how different is my prior distribution versus the posterior distribution. And they're trying to kind of superimpose these two distributions on top of each other by taking more and more samples and seeing when this converges. So that's basically what has been done. So if I give a bunch of configurations to start with, I can slowly start building the final Hamiltonian from there. That's an idea that we have taken and applied to some molecular systems and some model systems which look like molecular systems, like the ones that I showed before. With that, I will stop, but I will not show any of these, but I will give the acknowledgement slide, because my students, they did all of this work, and I should definitely thank these 4 students who are working on this project, mainly the ones that I talked about today. Thank you.
Thank you, Debashree, just being on time. Question.
Yes.
Yes.
Kind of systems.
Yeah.
I think the best way to go around is using inorganic complexes to self-assemble, because you can have different spins, like spin half, spin one, or whatever.
Yes.
Because I asked organic chemists whether they can synthesize anything like that.
Sized.
Is it?
Yeah.
Oh, okay. I didn't know, but they said just fused azulene is almost impossible because it's extremely reactive.
They are, but they have already been synthesized, some of them. So
Okay,
yeah.
I don't know which one,
Yeah.
because no, even I don't know how they do it.
We cited those papers. That's why, you know, I don't know anything of synthesis, but
Yeah.
Probably synthesis in vacuum. Very low pressure.
sorry, I actually don't know. I just saw those synthesis, got excited, cited them. Yeah. But actually, there's one system we are seeing some difference also. I should be honest here. So when we are looking at those, you know, those helicene kind of systems, which turns and rotates like this, there we are actually not being able to get any J or any Hubbard parameter to give the correct singlet triplet gaps and everything. As in, if we get for one system, for the other it breaks, which basically means I have not parameterized it well. So yeah. And I believe it's because there are those double bonds that are becoming fixed there. So there's not a full, delocalization throughout. Yes. That's my feeling. I can't prove it.
Hello, ma'am.
Hmm.
You use the RBM instead of tensor network. So I wanted to know what is the advantage of RBM over that network, tensor network, so that I can use tensor network already used, widely used, but what is the advantage of RBM so that I can use the neural network?
Basically, at this point, we are trying to converge, which gives the correlation as quickly as possible. See, if I have the least number of configurations or least number of samples to give me the final wave function, that's going to be my main goal. And for that, I'm trying out different approaches and seeing which one converges faster. For example, at least for RBM, we have seen that it converges faster than Monte Carlo. If I do a pure simple Monte Carlo on the configurations, this one converges faster than Monte Carlo.
But the number of parameter convergence, a lot of parameter is there in the RBM.
System size, the parameters are growing much faster than in tensors. Yes, you are right
Yes,
there.
then how it is converging faster?
At one point, you can start taking local approximations. For example, it need not be everything to everything connected. It can be next nearest neighbor or next nearest neighbor connected RBMs also. That's absolutely possible, because if you are writing the function by yourself, then I mean, you create your own function. That's possible, right?
Okay, okay, thank you.
There are no more questions. Thank you for a cup of tea, speaker and the lecturers. So can you come, Ritik? I mean, so these are the people who will take you there, the building. It is and then I think speakers will have a car. You will take them, and the students